Okay, so quick review. The early universe goes a little like this. This is Big Bang. After the Big Bang, the universe is way too hot for anything to exist. So this is just pure energy in this phase. And within the first second of the Big Bang, the universe has expanded enough such that it's gotten larger, and so it's gotten colder. And it's cold enough for some of this energy to get turned into actual particles. Particles are still ionized, though. They haven't. The universe hasn't cooled enough for these particles to join together to become neutral atoms yet. And so the result is that you have a tons of photons and a tons of ionized particles. These photons hit the ionized particles, so you'll see like a photon get absorbed by a proton here and then get re-released. And this process is happening all the time, countless amount of times per second. The photons are just scattering in every random direction. But at some point, the universe will get larger, and it will cool more. And as it cools, the energy of the universe, latent energy of the universe, will drop. And at around 100,000 years, suddenly the universe is cold enough for the atoms to combine and basically make hydrogen atoms everywhere. So now you have a whole bunch of hydrogen atoms that are just around the universe. You have some helium atoms, but mostly hydrogen. And suddenly, the photons, which were in this phase scattering, hitting particles, going off in every which direction, suddenly they pass through the atoms as if they weren't there. Because these photons are way too high energy, right? So the energy of them is way larger than the 13.6 eV necessary to go disturb an electron and raise it to the next energy state in the hydrogen atom. And so these photons, which no longer can get absorbed, now start moving freely throughout space. And in some cases, actually in most of the cases, they move through a vacuum without actually interacting with anything. They don't scatter, they don't hit galaxies. They could, but there's so much empty space and so many photons that actually a lot of these photons just keep traveling forever without hitting anything. But occasionally they do hit stuff. And if you waited another, approximately 14 billion years, sometimes they hit Earth. And after 14 billion years, eventually you'll have the Earth over here. And some of these CMB photons will eventually, we call them CMB photons because they get redshifted all the way to the microwave end of the spectrum. So when we detect them and when they hit Earth, they actually are in the microwave part. So, interesting fact, on old TVs that still have antennas, like they put antennas on the TV in order to catch whatever local TV channel there is, sometimes you get static. So if you turn on those old tube TVs that, they're like 30 years old at this point, if you turn them on, sometimes you get like that black and white static. And I believe the calculation is something like 1 to 2% of that overall black and white static on the TVs is actually due to these photons from the time of the early universe, these CMB photons, which are hitting your TV antenna, interestingly enough. So these photons go around and they hit things, and eventually they hit our telescopes on Earth, and we measure them. Now, the problem here is that the photons coming from every which direction all have the exact same temperature, right? So whenever we make a heat map of these photons coming from every direction, remember that our universe is actually three-dimensional, so photons are coming from every direction. If you made a heat map and calculated the temperature, remember, temperature just means kinetic energy. So if you went and calculated the energy or the amount of temperature that each one of these photons has when they hit the telescope, you'd find out that they have exactly the same temperature, within 10 to the power of minus 6 kelvins from one another. That means the brightest spots of these CMB photons and the coldest spots of these CMB photons are actually separated by basically nothing. It's even temperature everywhere. Now, as we've said, this can't be because if we calculate how much distance there is at this time over here, and if we were to calculate like how far a photon could have moved in that time, there's no way that the universe was in equilibrium. at this time, the time where all the photons were finally able to roam free without scattering off of these ionized particles. So what we want to prove over here mathematically is that there's no way the universe had enough time for these photons to be in thermal equilibrium with one another. And like I said in the last video, if you put a hot cake in a room, and if I gave the cake in the room, a few hours, eventually they'll come to a thermal equilibrium because there's enough time for the energy of the particle to come to equilibrium. In other words, there's enough time for the energy in the room to go back and forth and be transmitted back and forth at the speed of light. But if I put the cake and I put that in a room which was 10, light years big or 10 light years wide, it would take a lot longer because the energy of that cake needs to be communicated to everywhere else inside the room. And because the speed of light is finite, that's going to take some time. And the larger I make that room, basically the more time it's going to take for equilibrium to happen. Well, if you imagine the room as this early universe over here, so this is one-dimensional, right? But you can imagine this as being a three-dimensional box. And if I were to calculate all those photons, which I just said were emitted at the time where they were able to pass through the hydrogen atoms without having to hit an ionized particle, eventually, if I waited long enough, all those photons are going to interact with everything, interact with other photons, and eventually everything will come to the same temperature. Great. But if the universe at this point, this transition over here is way too large, you can imagine this universe as being absolutely gigantic. Or in an extreme, unrealistic case, you can imagine this universe as being infinitely large, let's say. Let's say it were truly infinitely large in that there's no end of space. These CMB photons would never be able to come in thermal equilibrium because there's infinite amount of space. So for the communication between temperature to balance out, there needs to be infinite amount of time for a photon to go from one end of the universe to the other infinite end of the universe and to finally come to some equilibrium temperature. And in that extreme case, it can't happen, right? If there were a finite sized universe, then maybe you can have communication go back and forth and there'd be enough time for that to happen. But it's impossible to happen for an infinite universe. Now, we don't have infinite amount of space, but space at that time was really, really large. And the CMB photons that we get today coming to Earth are all exactly the same temperature. So let's calculate then if there was enough time in that early universe for all those photons to come into thermal equilibrium based on the size of the universe and obviously how fast photons move. So what we're going to do then is we are going to calculate, number one, how far could a photon have traveled in the early universe? So what we want to know is, was there enough time in the early universe? So was there enough time in this region over here such that the entire universe was in thermal equilibrium? If the answer is yes, and if we found out that, there's enough time in the early universe from the Big Bang all the way to the CMB photons, if we find there was enough time in the universe for everything inside here to be in thermal equilibrium, then after these photons roam free, the CMB photons roam free towards Earth, then if everything was already in thermal equilibrium, then so be it, right? In other words, if everything came into thermal equilibrium before these photons were finally released at that boundary over here, then the thermal equilibrium just stays that way as it propagates towards Earth. But if we calculate that there was not enough time in this early universe up until the time where the CMB photons were released, then nothing was in equilibrium. And if nothing was in equilibrium, then when we get our photons all the way, when we collect the photons through our telescopes on Earth, we should find that there should be no equilibrium. But obviously that's not the case. We find there's equilibrium because it's 10 to the power minus 6 Kelvin that separates them. So let's confirm that with a calculation then. So our first one is going to be, how far could a photon have traveled in the early universe? In other words, we want to know what's the distance that a photon could have traveled throughout this time. And then we're going to compare it to the size. All right. to the real size of the universe. So as you remember, the space-time interval is given by this, and this is dr squared, or if you like dx squared, we can call this dx squared. But if you remember, co-moving distance was what we called the grid lines of the universe, which are painted on the universe and they're unchanging. In other words, the universe gets larger, these grid lines get larger with it, and that is what we refer to as d chi squared. Looks like an x. So it's basically this. Now, as you proved in your first assignment, photons move, or photons don't experience any space-time. They have ds squared equal to 0. So that means for a photon, then that 0 will be equal to minus dt squared plus a squared d chi squared. Remember, d chi squared is distance. It's the co-moving distance of the universe, so that is not something which gets scaled by the scale factor. If you want to find the real distance, you got to multiply by a. So for a photon, the amount of distance that's covered, d chi squared, is going to be equal to dt squared over a squared, like this. And if you take the square root, the distance that's covered, which is the left-hand side, is going to be dt over a. Okay. Now let's find the total distance covered by the photon. We'll have to integrate both sides. The integral will remove the d chi, becomes just a chi, just distance. And now let's calculate the total distance covered by a photon when it was emitted at the Big Bang. So this is the Big Bang, to the time when the CMB photons were released. The time when the CMB photons were released is this. We said it was 100,000 years. I'm just going to abbreviate that as TCMB, the cosmic microwave background. So this is really 100,000 years. And then dt divided by a. So as you know, a is a scale factor, and in the radiation era, that is t to the power of 1/2. This is a super easy integral. 0 TCMB t to the 1/2. Whoops. That's just dt over t to the 1/2. And when you integrate this, you will get times 2. Okay? So this is the integral, and then you'll have to put in 0 and TCMB. I just realized something over here. My dimensions make no sense. That's going to be c squared, c squared, c squared. Remember, time becomes a spatial dimension when you multiply by c. So this goes like this. Okay? Now, the factor of 2 over here is not really going to do very much to us. It's going to be more of like an order of magnitude. We're going to check to see if we're like 100 times off, 1,000 times off or something. The factor of 2 won't do very much for us. Anyway, so this will be t c to the 1/2 from 0 t CMB. And then we can just include the 2. Now, this is a co-moving distance. As you know, the universe is getting scaled as time moves on. The universe is going to get scaled every second. And so the true distance is L, and that is A times co-moving distance. And so this is going to be t to the 1/2 in the early universe, multiplied by chi, which is basically going to become 2ct t to the power of 1/2 plus 1/2. So this is just going to be 2 dt, which makes sense, by the way. And then when you plug in CMB you have 2ct times the CMB. This makes total sense, by the way, because this is just a distance. CT is basically like distance is equal to velocity times time, where c is the velocity and the time is the time where the CMB photons were released. Okay, so this is the total amount of this. Oops, there we go. This L is the total amount of distance covered. So total amount of distance covered by a photon from the Big Bang to when the CMB photons were released. All right. Now, if you compare this number, so if you compare this number, L, so we are going to compare L to the actual size of the universe at the time of the CMB. What you'll find is that the L, size of universe, is a factor of 10 to the power of 28 times larger than 2 times CT CMB, right? So what that means that the actual size of the universe, so L actual divided by L distance covered by photons, is going to be a factor of 10 to the 28th difference. So that means, if you want to think of it this way, that means that the photons could have covered a distance of only the photons could have covered a distance that is 0.000028 times, and then with the 1 of it, percentage of the universe is total distance. So that means if the total distance of the universe were like, making up a number over here, if the total distance of the universe was a meter, then the distance that the photons covered up until that time is 10 to the power of minus 28 of that 1 meter, right? So it would have traveled less than a nanometer, less than a trillionth of a nanometer. It would have covered nearly nothing. And so what that means is that there's not nearly enough time for the photons in the early universe, from the Big Bang all the way to when the CMB photons were released, for them to be in thermal equilibrium. There's no way they could have communicated on time. They would need something like 10 to the power of 28 more times, the length of time that had already passed, in order for a photon to go from here to the other end. And then they'd have to do this a number of times to actually come to some sort of equilibrium situation. And yet, when we get the photons on Earth, arriving on Earth, we find that they're the same in every single direction in terms of temperature. So our observations tell us that everything had to be uniform and everything was in thermal equilibrium. But then if you go through this calculation, you find out there's no way that the photons could have traveled enough time, that early universe, traveled enough distance in the early universe such that they came into thermal equilibrium. And that's the end of the what's called the horizon problem, second problem in Big Bang cosmology.